Hello and welcome to this lesson on entropy. It has specification reference 3.1.8.2. And in this lesson on entropy, by the end we want to make sure that we know that entropy, given the symbol S, is a measure of disorder. And we can also call it randomness or chaos. And we need to know that the universe tends towards randomness and chaos, i.e. increasing entropy. So as well as that, we need to know how entropy is affected by the physical state, i.e. solid, liquid, gas. Also dissolution, that's dissolving in water, and the number of particles. And that would be, for example, if a reaction starts off with 2 reactant molecules and turns into 3 product molecules, that would be an increase in entropy. And lastly, we want to just get mathematical about it and calculate the actual entropy changes in joules per mole. So here we've got a diagram that explains how its physical state affects entropy. And you can see that in a solid, the particles are very ordered and they don't move around much. They just move around a fixed point if they've got heat energy. But when they melt, the particles, although they stay quite close together, they move around a lot more and they're not fixed in one position. And so you can see that the liquid is much more disordered. The particles in a liquid are able to move around much more, and that means that the liquid is more disordered, and that by definition is a higher state of entropy. And then when the liquid boils, when the liquid boils, the particles are very free to move, and they've got large distances between them relative to their sizes, and that's quite chaotic, and even more entropy is contained in the gas, because those gas particles are spaced apart and moving fast and moving away from each other all the time. So that disorder has increased, and that means the entropy has increased. So secondly, we're now looking at how the process of dissolving increases entropy. And of course, when the solid is not dissolved, the particles are in fixed positions with low entropy. But when they're dissolved, their ionic bonds have been broken, and they're now free to move apart in the solution. And so obviously they've got much more disorder, and so their entropy is higher. And lastly, when we have a chemical reaction like this decomposition reaction, where the 6 dinitrogen tetroxide molecules have decomposed into 12 nitrogen dioxide molecules, you can see that there's twice as many product molecules than there were reactant molecules. And because the number of particles is increased, that means that the entropy has increased. So let's look at a couple of examples. First one is when water evaporates, entropy increases. Why is that? Well, let's have a look at a diagram. When the water is a liquid, then the particles are moving around slower than they are when they're gaseous, and they're less chaotic. But when they evaporate, there's more chaos in the water molecules, and so the entropy is higher. Another example is when sodium hydrogen carbonate reacts with hydrochloric acid. The entropy increases there. Why is that? Let's have a look at the balanced equation. So you've got your sodium hydrogen carbonate here, your acid particles from your hydrochloric acid. And when that reacts, we get sodium ion, a carbon dioxide molecule given off, and a water molecule left around. So you can see that there are 3 particles here and only 2 particles on the reactant side there. So the number of particles has increased, as you can see with this diagram here. So if we had, looking at the left-hand beaker, we've got 1 mole of solid sodium hydrogen carbonate and 1 mole of hydrogen ions. But on the right-hand side, we've got a mole of sodium ions, we've got a mole of water, and we've got a mole of carbon dioxide gas being given off. So as you can see, the entropy has increased for 2 reasons. 1, we've got more particles, and 2, some of the particles are now gaseous. So let's get a bit mathematical about entropy just now, and we have a little example to work with. Here we're going to calculate the entropy change for the reaction of ammonia and hydrogen chloride rather, under standard conditions. Okay, so we've got ammonia and hydrogen chloride gas going to ammonium chloride. Okay, so the first thing we need to do is recognize that it's asking for an entropy change. So what we're going to do is we're going to use a formula for that entropy change. So as you know, the delta stands for a change in, and S is entropy, so delta S means entropy change. And entropy change is just quite simply the total entropy of all the products minus the total entropy of all the reactants. So we can write total as in sum of the entropy of the products, right, is minus the total entropy of all the reactants. That's the formula we're going to use, and you do well to remember it. So in this case, on the right hand side, we're given all these values, and just a reminder that here we've got standard conditions, all right, which means we're dealing with 1 mole of each substance. And plugging in the values, if we look at our product is our ammonium chloride, and that has an entropy of 94.6 joules per Kelvin per mole. And then we're going to open our brackets because we're going to add up all of our reactants. So the entropy of our ammonia is 192.3 joules per Kelvin per mole. And our other product is hydrogen chloride gas, and as you can see, the entropy of that, in 1 mole of that at standard conditions, is 186.8 joules per Kelvin per mole. And when we do that calculation, we've come up with a negative 284.5. Right, let's be careful about the units. Joules per Kelvin per mole are the units of entropy change. And last thing to notice about this is the negative sign there. So that means that there's less entropy in the products than there was in the reactants. And that's, if you look back conceptually at the reaction, you've got 1 mole of a solid versus 2 moles of a gas. Two moles of gases. So it's not surprising that the entropy of the product is less than the entropies, the sum of the entropies of the reactants, giving yourself a negative entropy change. Okay, let's just recap to finish off with. And do we know that entropy S is a measure of disorder? Yes, I think we do. And we could also use the word randomness or chaos instead of disorder. Do we know how entropy is affected by physical state? I think we know that entropy increases as we go from solid to liquid to gas. And we also know that entropy increases as we dissolve a solid in a liquid, which is usually water. And we also know that entropy increases in a chemical reaction if the number of particles of products is more than the number of particles of the reactants. And lastly, we calculated an entropy change for a reaction, and we will remember that the entropy change is just the difference between the entropies of the products minus the entropies of the reactants. So there we are. I hope that's been clear for you.